All right, let's jump right in. What if I told you that you could solve some of the gnarliest problems in quantum physics, but without a quantum computer? It sounds kind of wild, right? Well, we're about to dive into a super fascinating idea that does exactly that. And the secret? It's all about looking backward, at classic tech, to build something totally revolutionary.
So it really all comes down to this one question. We're always thinking progress has to mean newer, smaller, faster, right? But what if the key to unlocking the next big thing in computing has been hiding in plain sight, in principles we figured out decades ago? Well, let's dig in and find out.
So, where does this whole story start? Well, not where you might think. We're not in some fancy, state-of-the-art quantum lab. Nope. We're starting with a basic building block of classic electronics, an idea that's really all about finding a perfect balance, even when things get noisy.
Okay, imagine you're trying to hear someone whisper to you in a really, really loud room. It's almost impossible, right? Well, a differential amplifier is kind of like having two ears or two microphones. It listens to everything, the whole noisy room with both. Then it does something brilliant. It subtracts out all the identical background noise that both mics are hearing, and what's left over? Just that tiny little difference between them, the whisper. It's an absolute master at finding the important signal by creating this perfect balance. And that is the huge leap in thinking here. Instead of calculating an answer one step at a time like a normal computer does, what if you could build a physical network that just settles into the right answer all on its own? You'd have a system that uses its own physics to find the most stable state, the ground state of a quantum system, just by naturally balancing itself out.
And that right there is why this analog approach is such a game changer. See, a normal digital computer, it simulates the math behind a system. It's a number cruncher. And that takes a ton of energy, and you hit a wall really, really fast when problems get complex. But this idea? It's totally different. It doesn't simulate the math. It physically builds a model of the physics. You're letting the laws of nature do the hard work for you, which makes it unbelievably efficient for certain kinds of problems.
Okay, so this idea of a self-balancing network is amazing, but how do you build it so it doesn't just turn into a chaotic mess, right? You can't just connect a bunch of things randomly. You need a blueprint. You need rules. And this is where a truly brilliant mathematical insight comes in and just changes everything.
This was the aha moment. The quote says it all. The idea wasn't about a physical box. No, it was about a mathematical one. What if you use the elegant, perfectly balanced structure of a magic cube, or, get this, even a multi-dimensional hypercube, to lay out all the connections and rules for the whole network?
Now, it's super important to get this. We're not talking about a literal cube made of wires and chips. It's an abstract idea, a blueprint. You know those magic squares from math puzzles, where every row, column, and diagonal adds up to the same number? Well, imagine taking that concept, that property of perfect built-in balance, and just scaling it way, way up. That becomes the design principle for the entire circuit, basically forcing it to find a stable solution. And using this kind of mathematical structure gives you some huge wins from an engineering perspective. For one, it makes the physical system naturally stable. It also gives you a really elegant way to define potentially billions of connections without it becoming a complete nightmare. Plus, the structure itself is naturally resistant to small errors, and it gives you a clear roadmap for how to scale this thing up to build even more powerful simulators in the future.
Okay, so having a beautiful math idea is one thing. That's great. But how do you actually take that abstract concept and turn it into a real, physical microchip? How do you forge it in silicon?
Well, it basically happens in 4 key steps. First up, you define your problem using that magic hypercube math. Step 2, you translate those mathematical rules into a network graph. You can just think of it as a map of dots and the lines connecting them. Third, you actually build that map in the real world using simple electronic parts. And finally, you give the whole thing a smart controller, an FPGA, which is basically a chip you can reprogram on the fly to manage everything and keep the network perfectly balanced.
Now, the actual physical building block for all of this is surprisingly simple. It's called an OTEC-C circuit. The most important part is the OTE. That's an amplifier where you can actually tune its strength just by changing a voltage. The best way to think of it is like a tiny programmable knob or dial. And these little dials are the connections in our network. By twisting them all to the right settings, we can literally program the chip to model all sorts of different quantum systems.
Okay, I know this all sounds really complex, but here's where the real genius of this whole thing clicks into place. It's not just about the tech, it's a huge shift in philosophy.
It's about realizing that for the kinds of problems we actually want to solve, trying to create a perfect, one-to-one, full-truth simulation isn't just impossible, it's actually the completely wrong thing to be aiming for.
And this really gets to the heart of it. Think about a scientist designing a new drug. They're trying to figure out how a molecule will behave. They don't need to know the exact state of every single particle at every single nanosecond. That's overkill. What they need are the important bits, the properties of the final stable state. That's the answer that actually matters in the real world.
So, you can think of this system as an answer engine, not a universe simulator. It's designed for one purpose: get the useful answer. And by focusing only on what matters, it completely sidesteps that insane complexity that makes quantum mechanics so hard to compute. And the most beautiful part? That magic cube structure we talked about, it naturally guides the network to settle into those low-energy stable states, which, 9 times out of 10, are the exact answers the scientists were looking for in the first place.
All right, so we've got the science down and we've got the philosophy behind it, but how does this become a real product you can actually sell? Let's switch gears a bit. For this last part, let's imagine we're pitching this whole concept to a team of top-tier chip design engineers.
Okay, team, here's the pitch. We are building a dedicated computing accelerator. The core idea? A chip that physically models systems instead of calculating them. The value proposition is insane speed and efficiency for a very specific set of high-value problems. Think drug discovery, material science. The secret sauce is that magic cube math that guarantees stability. And here's the real kicker. We can build the whole thing on mature, reliable, and super cost-effective chip technology.
Naturally, the engineers are going to have questions, right? So, what's the target market? That's a multi-billion-dollar space. Drug discovery, material science, academic research. What's the core innovation here? It's the tight fusion of the analog hardware with the software that maps the problems onto the chip. Okay, what manufacturing process are you using? And this is where it gets really, really smart. We're not using the latest 5-nanometer tech. No, we're using mature processes, like 28 or 40 nanometer.
And this is where you see this totally counterintuitive, brilliant piece of engineering. Because for analog circuits like these, newer is not always better. Turns out, the bigger transistors on those older chips can handle higher voltages. That means you get a stronger signal and less noise. So, for what we're doing, older tech isn't just cheaper, it actually gives us better performance. It's a win-win-win.
And really, that brings us full circle. This whole concept is just amazing proof that innovation isn't always about chasing the newest, shiniest thing. Sometimes the biggest, most profound breakthroughs happen when someone looks at an old, established idea in a totally new way. It just makes you wonder, right? What other revolutionary ideas are just hiding in plain sight, waiting for someone to connect the dots?